All right, so I'll try to be really quick and just explain some of these ideas, and hopefully they'll be useful for people building blockchains right now, but as well if you're building a project and you're shopping around for particular rollups or blockchains, this is sort of a presentation, for you. So today I'm going to talk about real-time blockchains, which is quite frankly something we all just made up recently. So it's another term. We just made it up, and there's no fundamental basis for it other than the fact that real-time has some meaning in Web 2, and it's somewhat relevant to the conversation for technical architecture for Web 3. So effectively, imagine a world where blockchains were actually real-time by virtue of what you see in the web. What does real time mean? Typically, it means like less than 100 milliseconds. So right now, like Solana's block time's at 400 milliseconds. So you can imagine, okay, well, how could you get that a lot faster, more regional, something where you can actually do a lot more sophisticated work around the world and do it in a way that won't interrupt the user experience for 90 to 95% of users. So 100 milliseconds, real time. That's sort of what we mean. So typically in the span of what we mean by timing and as well just the life cycles of transactions, et cetera, there's some different notable times that you can actually see in blockchain itself. So hitting an RPC, usually for a user, like anywhere from 100 to 200 milliseconds, depending on where it's located. Solana slot times at 400 milliseconds. Fuel, my project, our layer 2 finality sitting at around 1 second. Cosmos finality sitting at around 6 seconds. Ethereum block times at 12 seconds, and Ethereum finality at around 13 minutes and two epochs, something like that. So there's a sort of wide spectrum of time that means different things for different users on different blockchains presently. And effectively, if you really want to make a user experience that's incredible, but you also have many different rollups and many different blockchains, and you need to communicate a lot of different information, potentially over a global sphere, this becomes really complicated because things are just too slow, typically, for the kinds of user experiences that people want. And I'll explain why it's too slow. So if you look at like this is just an average of global ping times, and it's from location to location, basically you can see that if you're roughly in a similar region, like the EU West, for example, like if you're going from Stockholm to Paris in terms of your ping time, you have like a pretty decent ping time, like around 30 milliseconds. But if you're going from, say, like Los Angeles to Tokyo, then your ping time starts to increase. Then it goes to 107 milliseconds. If you're going from Frankfurt to Tokyo, then here's where the real problem starts. You have about 254 milliseconds on average. So the problem is like if you want to build a global blockchain, or you have a project that wants to be globally accessible, and you want the times to be very, very fast, you're really fighting actually just physics and the ocean to be able to come to consensus just because of ping time, which is really, really simple. Your signal can't traverse the Earth fast enough to really get everything done because it's not just communicating any bit of information around the Earth, it's also you have to come to consensus over what's been communicated, and it's very, very difficult. And so basically, you could see why a team like Solana would set their block slot time to around 400 milliseconds because you literally can't chart the Earth very quick in general, and you need to leave enough time to actually execute all the transactions. So we kind of have a big problem here in terms of if we want blockchains to go faster and do more sophisticated things over more sophisticated environments, we're kind of fighting physics in order to achieve this. And here's like a really good kind of diagram from he.net where you can see some of the undersea cables for connecting different places on planet Earth right now. And you can send some pretty sophisticated signals all the way around the world. But again, you're fighting physics in terms of just how fast that can actually happen and how fast you can actually traverse the Earth in order to produce the speed that we're really looking for. So we have a lot of problems. If we want blockchains to be really, really fast and we want them to be highly available, we're going to be fighting physics, basically, in order to achieve what we want to get done. So like, what does really fast blockchains, well, who really gives a shit if it's 1 second or 400 milliseconds or whatever? Isn't that fast enough? And you would think, yeah, that seems totally fast enough. 400 milliseconds, whatever, that seems like it's a pretty good time. But you're not factoring in the fact that the blockchains are becoming a lot more complicated. There's a lot more actors, and those actors are very sophisticated, and they actually need really, really fast communication time, also finality, et cetera. They need everything to speed up a lot. So some examples of like what I'd call like real power users of blockchain are block builders, solvers, relayers, data infrastructure, market makers, and provers. All these parties actually need things to speed up a lot because they need to get the information to just do whatever they want to do. Market makers need it to be able to actually assess the current state, the view of things, and make trades. Provers need it so that they can send it out to all the different ASICs that are available, you know, in 2, 3 years from now. They'll still need to send out all the information to actually prove somewhere that, you know, hey, this is actually the state of things, or this is actually how things become final. So it's a real issue for these people. And as blockchains progress and as architecture progresses, we're going to be hitting some real serious issues. And basically, 1 second to 400 milliseconds is not really going to be fast enough. So, you know, and if we look at the two different kinds of users, regular users versus just like the power users, regular users don't really care. So, you know, 400 milliseconds to 3 seconds doesn't really matter. You know, 0.1 to 1 cent price target, all that doesn't really matter. They're not particularly sophisticated. Most of these sort of regular users don't really care. But for the power users, they actually need they need a lot faster speed to be able to get all the work that they want to do done. 400 milliseconds is way too slow. It requires more of a real-time view, so under 100 milliseconds. As well, the price target of even 0.1 cent is far too high for a lot of those actors. And as well, they're highly sophisticated. So they're typically running servers on T1 lines in, you know, well-positioned locations. For them, all the time that you spend just doing random gobbledygook is actually really affecting how they operate. So when you look at just like typical sequencer designs right now that are coming up, particularly in the rollup space, you know, you have the transactions going to builders. Builders are working with sequencers, and then it's going to rollups, and it's actually being proved, or you have fraud proving, so you're in an optimistic setting. And then eventually, at the end of the day, it's ending up at Ethereum. This is a typical trajectory of what we see with the current sequencer designs right now. And the problem is, as I described before, there's some really big physics issues going on with just the trajectory of how that is actually unfolding for teams. So even just going from the transaction to the builder, you're already at anywhere from 10 to 250 milliseconds, depending on the location right now. Even that is already too slow. So for these builders, they would love to receive things a lot faster so they can actually execute things in a more efficient way. And then as well with provers, similarly, you're also going to have a very long time between something like, say, rollup finality post the challenge window versus like in a world where we had ASIC FPGAs and, you know, these other things for ZK, like you know, effectively you're still going to want the information as fast as possible to prove it, and then you have to go to Ethereum layer 1 at the end of the day if you're really, really fast, and again, you know, we're talking about a long span of time for effectively those power users that I was talking about before. So even if you have FPGAs and ASICs for ZK right now, just to get all the information to build the view and actually send all these proofs around is going to be something that needs to happen much faster than the way that we're currently designing the chains right now. Settlement is far too late. So looking at like Ethereum or Solana settlement times, et cetera, it's just far too late in the game for the amount of communication that needs to happen in order to efficiently build blocks in a blockchain itself. So we're going to run into a lot of issues if we don't actually figure out how do we make this system a lot faster. And even if you just consider rollup finality, so just when transactions have been received and could be even considered final in the rollup phase, it's still too late. So even with Fuel's current rollup time, finality time of 1 second, it's still even too late for a lot of block building applications and everything else. If you're also thinking about the time that it's going to take to process, say, 5,000 TPS over like a really, really short period of time, and then also building those blocks and then getting them out and finalizing them. So the pipeline really, really sucks. A concept that's been applied from the Solana side is basically that you have this global network, and then you provide these global locks on different aspects of state. So you lock it off, and then that's how they're trying to achieve sort of the guarantee or assuredness that state transitions are going to happen in a global context. The problem is those signals have to go all the way around the Earth in order to actually come to consensus. And so, unfortunately, just global locks alone on different pieces of state, say locking off one section over in Asia and one section over in America, it's going to be really tricky unless you design for it. So global locks just in and of themselves don't work. And again, coming back to this ping time chart, we're working with timescales here that really, really suck if you have to go all the way around the ocean. So unfortunately, you have to come up with some kind of solution that's more regional. So one idea that's been sort of floated around to get these, sort of the view and the communication improved for blockchains is effectively to have different leaders in different places. So you could have a leader in Asia, a leader in the EU West, a leader in the EU East, and basically when they're building and they're leading the chain, effectively this is going to allow you to have sort of faster block times, at least for those users. The problem is that you could easily commit a double spend here if you don't have the right kind of BFT system, and that's going to cause you some significant problems, obviously, because the whole point of a blockchain is to prevent double spends, so you're going to run into issues. So some possible solutions to kind of improving the regionality of blockchains and improving the actual speed of blockchains. So there's been some interesting designs in the past that are somewhat notable. Avalanche's leaderless BFT consensus is an interesting choice, potentially because if you have a more leaderless system, maybe you can get leaders closer to where the users are, and then maybe you can build blocks faster. There are a lot of caveats, though, to how that actually ends up working. As well, Say had some stuff with twin turbo consensus, which is quite frankly all marketing jargon. It's BS, but the point is, at least they're trying to think about more regional subcommittees that are going to form and actually process transactions. As well, Espresso has some notable ideas about sort of using very fast blockchains for sequencing, and they're more sensitive to these times as well. There's also happy path and sort of like fallback path style designs that, in the happy path everything works, in the fallback you go to a much slower peer-to-peer consensus. And then there's also things like execution tickets, which is basically just trying to speed up the whole process and say, well, if I'm the leader and I'm the block builder, I'll give you an execution ticket to say I've executed the transaction even before I've published or built the block. It's just I've executed it, it's going in this order, and this is where things are happening. So in Web 2, I've got 18 seconds. I'll try to go through this quick. In Web 2, how do we deal with this? Well, we have user-defined regionality. So users pick a region. If you're in Tokyo making a Visa payment, you're defining yourself there. So you're going to be settling within that region. You have edge computing, and then you have things like ACID transactions. All these things are going to be used to try to come to consensus quickly in a more regional setting. Basically, to skip over some of the ideas, the idea is that if you have builders in different regions, and they're coming to consensus in their own way, but you have users that are basically saying, hey, I'm over here in Asia, and I'm not over here in America, if you're really, really time sensitive, or you have a time sensitive user, this is the way that you can actually kind of block off different builders in different regions, and you can actually reduce communication overhead significantly. And yes, the builders have to communicate eventually to lock off certain aspects of state, which is going to be a little slower, But the idea is that for a user, you can actually get this execution ticket down to about 10 to 100 milliseconds if you're within the region of where those users are. So locking things off actually works really, really well. And you would have regional builders, then you'd have global builders. The global builders, it's a little slower. Maybe it's 400 to 1 second. But for the regional builders, it's very, very fast. You just need to, as a user, so to say, hey, I'm over here in Tokyo, or hey, I'm over here in LA, and then the applications can adjust depending on the region and depending on how you want building to happen. And so effectively using more regionality, like edge computing, you can bring down execution ticket time significantly, which is really great. So there's some key benefits here. Builders have more regionality. User preferences are defined in more regional terms. And basically what this means is that we can have these global blockchains, but if your app is really time sensitive, like an order book, you can bring the users over to that more time-sensitive region, and you can have users participating in that more time-sensitive region. The NASDAQ does something similar where they make all the cables the same length between all the high-frequency trading firms because they figured out eventually that the physical distance of the cable to where the FPGA is in New York actually mattered as to how things were being processed. So speed and regionality actually really, really matter. Your positioning really matters. At Fuel, we care a lot about speed. We're building very, very fast stuff with Fuel. We have what we define as the best rollup OS for Ethereum and the best rollup OS for blockchain itself. So if you're building things that want to go very fast, a lot of TPS, with no bullshit, and actually have real, genuine fraud proofs through and through, definitely check us out. We built the first optimistic rollup for Ethereum and launched that on mainnet. We've done it before. We'll do it again. And thanks, everyone. Really, really great chatting.
Thank you.
Thank you.